electrolytic refining plant that may be as big as an acre. We hang them in sulfuric acid containers, and in between each one of these anodes that we hang, we put a starting sheet of pure copper that we've gotten down the line as pure copper. And then we pass a current through it, and we get plated from the anode, which is impure, to the cathode, now pure copper. And in the process, we will drop out all of the noble metals, and the selenium and the tellurium. And so we get gold and silver and platinum, palladium, rhodium, iridium, selenium, and tellurium. When ASARCO used to have its plant in Baltimore, and he used to refine about 400 tons of copper a day, and out of that 400 tons of copper, they got enough selenium and tellurium to pay for the operation, or at least so they'd said. And they still got, at that time when gold was selling for $35 an ounce, they still got $18,000 worth of gold out of each 400 tons, and lots of silver and lots of other nice things. But when they're through with this, all they're really going to have now is a bumpy looking plate about the size I am, about 5 feet tall and about 3 feet wide. And that particular material is going to be a bubbly, blistery looking material. It's going to have some hydrogen in it because we're also going to decompose the electrolyte a little bit and plate it with some hydrogen. And so we put it back in a casting house, melt it again, and cast it. Now when we cast this particular material, we have an option of casting it in little ingots like pigs of iron, which we do. We could cast it in bars, let's say, that are just amenable to do processing on, rolling and drawing and making tubes of it and whatnot. Or we may cast this material as one continuous bar. We may have continuous casting. Now I'm going to describe the continuing casting for you with copper, although I hope you realize that the continuous casting operation is now carried out in the steel industry as well. And so back when we were talking about refinement of steel, we could have had continuous casting. But let's talk about the copper process.
One question about the electrolytic refining. Why do you try so hard to get the sulfur out if you're then going to take these billets of copper and drop them into sulfuric acid? It seems like any extra sulfur would just, disappear into the solution when you're electrolytically refining it.
You're asking me if I can win the material from the solution by, let's say, just electrolytic plating. And the answer is yes, I can. It just turns out it's more expensive to do it that way.
All right? So the electrolytic stages.
This system is the cheapest way to do it. You could do it another way, yes. You could take the ore and get the copper ions out of it in solution and plate them out of the solution, all right? You could do that.
Well, how about just skipping this converter step is, I guess, really all I'm suggesting. I mean, you've already got a substantial amount of copper.
Yep.
And mostly the converting step is getting rid of sulfur, apparently. But well, isn't the sulfur
it's going to be enough trash in it now to color the whole process to defeat the rest of the process. So you got to get it all in. You're going to get it to be pure copper. 99.99% copper. Very pure copper. Well, we don't get it that pure until it goes through the electrolytic process. Well, let's define this casting operation. If you can conceive of a great big wheel rotating that has a trapezoidal, like a V-belt cut in the middle of it, and visualize it operating on one side is a stainless steel belt, a wide belt that's running against the surface of that wheel so it closes a cavity. In between there's a cavity, a trapezoidal cavity. If we melt the molten material, if we get the material molten, the copper material molten, and pour it in that cavity between the two, and water cool the wheel from one side and from the other side, in one case the wheel, in the other case the little stainless steel sheet, which is rotating around belts, so we have a continual closure at that point. And we keep that stainless steel wrapped around the wheel to some exit point when it comes off and returns. Then what we will have is a solidification process that's continuous. We pour molten metal in one end and we get solid metal out of the other end. And we get a bar that just keeps on coming. And if we can do that in an optimum condition, then what we can do is put that right straight in a rolling mill and reduce it, this cross-section, trapezoidal cross-section, to rods and wires or even tubes on the other end. So it would just flow continuously through. Because of generally just problems, what happens is they will do that and they will roll the wire down to, say, something like a 1/4-inch copper wire to be redrawn at a later stage. So that's what the copper operation is. That's the operation that produces for us this beautiful material that we have that's called man's newest old metal, or man's oldest new metal, because we almost can't do without the copper. We use so much of it.
Early stages of extractive metallurgy involve comminution, flotation, and pouring the metal-containing slurry over a rotating disc, followed by drying. Roasting, matte smelting, and converting are intermediate steps of extractive metallurgy. Late stages of extractive metallurgy, fire refining and electrolytic refining, improve the purity of the metals extracted from the ore. Continuous casting is a popular final step in extractive metallurgy today because it makes possible rolling the cast strand directly into rod, bar, or wire.
Let's look at another process. Let's look at the aluminum process. And I have to tell you that many people have the mistaken idea that we didn't have any aluminum before Charles Hall appeared on the scene. And this is not so. Charles Hall did get the patents on the thermal electrolytic or pyroelectrolytic process for producing aluminum. But prior to that, aluminum was being made, particularly in France, and it had been identified some 40, 50 years before that. But we had a hard time developing it into a metal. That's because the heat of oxidation of aluminum is very, very high, extremely high. It forms the oxide so readily that it's hard to break that bond with the oxygen. We just cannot do that. So we do something like get the aluminum in a form, let's say a chloride form or some form, that we can use a material that has a high affinity for the engaging atoms. So if we use, say, molten sodium with molten aluminum chloride, we may get sodium chloride and aluminum out of it, right? Not a very satisfactory process, but it would work. And so we find that in France they produced aluminum before Charles Hall did. And in fact, the first aluminum that was ever produced at that particular time was a precious metal. Nobody ever had any before. So they made a baby rattle out of it, and it became, and is still part, I understand, still part of the crown jewels of France. And even in time we moved to the point where they were making that in this country. A rather nice amount of this kind of aluminum in this country. And the cap on the Washington Monument in Washington, D.C. is made of aluminum. And it was cast not by the Hall process, but before that in Philadelphia. So we did have aluminum, but we couldn't get the price of it down. It was very, very expensive to make. And so what Charles Hall did was he found out a way to produce it very cheaply, and founded, of course, what is today the Aluminum Company of America. Well, let's look at the extraction of aluminum just briefly for a moment and see what we're going to do as a necessary first step. If you want to refine aluminum, what you have to do is refine the ore to oxide. But you notice now we've been talking about doing that right along, even in the gold. So over here, on this part of the chart, we have a process that primarily has to do with purifying the ore, not getting the metal into an elemental form. The trick here is that we're going to use the ability of sodium hydroxide to dissolve aluminum oxide. As I told you in an earlier lesson, if we had a sphere of aluminum that was a single crystal and dropped it in sodium hydroxide, then the sodium hydroxide would dissolve the oxide from the surface of aluminum, corrode it, but it would eat it back into a little cube, because that's the shape that it most likely is to occur in, is a cubic form. Well, that says that there's a process for dissolving aluminum oxide. And the process is called a Bayer process, spelled just like the aspirin, Bayer aspirin, except it's the Bayer process. And in the Bayer process, we take the bauxite ore, which is a combination of iron oxides, silicon oxides, and aluminum oxide. And we treat it, we grind it up first of all so we can dissolve it, and then we digest it or treat it with sodium hydroxide, caustic soda solution. And we take this caustic soda solution now, which is going to contain the alumina as a sodium aluminate, and we filter it. And what we filter out is a red mud. That red mud will contain almost all of the silica and all of the iron, or virtually all of the iron. Because these particular materials don't dissolve readily in the sodium hydroxide solution, the concentrations we have. Having filtered it out, now we have to precipitate that particular aluminum oxide from the solution, and we do that in a precipitation tank. And we have to filter the material, and then we evaporate off the sodium hydroxide solutions, and they're carried back to the digester, and this continues to go on over and over and over. So somewhere out there where the ore is concentrated, Jamaica or wherever it might be, we're going to have digestion plants that are going to digest the bauxite ore and produce this very, very beautiful, pure, white powder that is aluminum oxide. And that is necessary if we're going to refine aluminum, because it is almost impossible, once something gets in the aluminum, to take it back out of the aluminum. We take this particular material now, which is the aluminum oxide, and we calcine it. It's going to be wet. The calcining operation is now the operation that we discussed before, where we're just going to drive the water off, and essentially, and we're going to get the alumina out. And this particular alumina, we're going to use the Hall process. And all Charles Hall did was to find out, well, he knew beforehand that he couldn't melt this aluminum oxide. Its melting point is very, very high. If he gets it molten, he can't just electrolyze the aluminum out of it. So what he found out was, if he uses cryolite, that's a sodium aluminum fluoride, a mineral that we can produce synthetically, but we find in nature. If he took this particular material, fluorite, this cryolite material, and put the aluminum oxide in it, it would dissolve. And then we can plate out the aluminum electrolytically from this bath that's molten cryolite with the aluminum oxide dissolved in it. And when we do that, then the aluminum falls to the bottom of the pile. The top of the pile, which is on a carbon electrode, receives the oxygen when we break up the aluminum oxide, and it burns and supplies some of the energy to keep the pot hot so we can handle the molten aluminum. And we tap out the aluminum, and we are able to produce it in, cast it in aluminum ingots, or continuously cast it, or make it into powders, or do whatever we want to, roll it into structural shapes. So that's the Hall process, and that's the process that's called the pyroelectric process, or the thermoelectric process. But let's for a moment just look at a little problem that Charles Hall had. I think it's interesting to look at this because it helps us appreciate the problems we have in a lot of the industry, of all industry today. Actually, Charles Hall was a very meticulous man, and he's not the first person to discover how to refine aluminum by this process. The man that learned to do this is Herhold, and he is a Frenchman, and he was a pyroelectric man, worked in that field. But there's a difference in the personalities of these two men. Herhold was a man that was given to having a good time. He didn't worry about keeping notes. I guess he wrote them on the cuffs of his shirt and then they got washed away. He was a ladies' man. He was forever carousing around, I understand. So he wasn't a good bookkeeper. But he did invent this particular process. Charles Hall independently, very shortly thereafter, invented the process. And he's the son of a Presbyterian minister, very meticulous, kept notes. The first Sunday he succeeded in doing this, he got a little tiny piece of aluminum. He wrote a letter to his sister and sent her this piece of aluminum and said, you know, look what I did today, right? It's precious metal now, remember, up there. And so